Okay, hi again. Today I'll be going over parts 2D and 2E, so how to use prior physical knowledge to actually constrain the model building process, and then how to use what's called trapping SINDy to actually promote globally stable models. These are fairly more advanced techniques that can give you some robustness to noise, but if you're not super familiar with PySINDy, I don't recommend them because they are a little more difficult to use and a little more subtle to understand what's going on. And I'll talk about that as we go on. The first thing we're going to do is just define a regular unconstrained by physical knowledge model. And we're going to use the SR3 optimizer for this so that we can compare to the constrained results later. So we're going to use SR3, some threshold value, some lambda value. Again, let's just define a model and fit it. So our normal thing, put in our Lorenz feature names and our optimizer. We're going to fit that model with the training data. Let's actually use our noisy data. Let's see, good. And just so we know what we're looking at, let's say SR3 model, no constraints. And then model.print. Good. Okay, so with this amount of noise, SR3 sort of roughly gives the right values, but it's got some extra terms. You can see some extra terms on this these constant terms in the front. So it's doing an okay job with this noise, but it could be better. So now we're just going to repeat that, but we're going to use the constrained SR3 optimizer to actually build in physical priors into the system. And for this, the priors are going to be pretty simple. But before I do that, let me just simulate this model forward so that we can compare these models at the end. So we're going to do model.simulate with the initial condition for the test data and the time series for the testing data. So they'll just generate some simulation data for a new trajectory. So we do that. Now what we're going to do is let's see. Okay, so we're just going to define n targets as 3. The number of features in our candidate library, you can count up how many terms are in the candidate library. Turns out it's 10 because we have up to quadratic and polynomials for these three variables. And then we're going to define a right-hand side of the constraints. So in general, the constraints, if I can write this somewhere, are going to look like C times C equals D. Okay? So we're putting affine or linear constraints on these model coefficients in C and then still solving that optimization problem as before. So for the right-hand side, we're going to do lumpy as array 0 and 28. I'll explain what's going on in a second, but I need to make these definitions. So we're going to have 2 constraints. So 2, and then the dimension of this is the number of targets times the number of features. Now we need to define what each of these are. So let me just write these down, and I'll explain what I'm doing in a second. It'll be a little more clear. And then constraint left-hand side 1 plus n features equals 1. Okay, so this first constraint is basically saying that I want the coefficient of x and the coefficient of y to be equal and opposite in equation 1. So in other words, I want this in equation 1, I want the coefficients here to be equal and opposite, which you can see in the true Lorenz system they're minus 10 and 10. So I'm just going to put that in as a prior that I already know about the system, and have that be directly built into the model, so I don't have to discover it. And then this one is the coefficient of x in the second equation will be equal to 28, right? So I put a 28 here and a 0 for the first. So that will be, so this one, this first constraint is x plus y equals 0. The coefficients of x and the coefficient of x plus the coefficient of y equals 0 for the first equation. And the second constraint is that the coefficient of x in the second equation equals 28. Right, and again, that's what we expect for our Lorenz model. So we're sort of building in things we already know about the system. So that's great. Now what we need to do is define our optimizer with these constraints. Again, need to do PySINDy.constraint SR3. We're going to put in exactly the right-hand side and left-hand side constraints that we just defined. Again, so that we can compare with the previous model that was unconstrained, let's use exactly the same threshold, and let's actually make these all use the L1 norm for a regularizer, since it's a little easier. So I need to go back here and change this to L1 as well. Okay. So rerun that, it's about the same, and then this optimizer is now defined, and we can do exactly the same thing here. Fit the model, simulate a new trajectory on this testing data, and so we're fitting the data. We have this optimizer. Oops, I forgot to make the actual SINDy model, and that should work. Okay, so this is the SR3 model with no, the constrained SR3 model with inequality constraints. With equality constraints, sorry. So that's great. That's what we get. And now I'm going to repeat the same thing, but now using inequality constraints. And I'm going to compare these three methods. You're going to see there's some stark differences. So let's just copy and paste this. Whoops. This whole thing over. So it's cell below. Okay, the main difference here is that we have to explicitly tell the model that we're using inequality constraints. So we have a flag that you set to true. So that's good. And then we're going to actually have three constraints. I'll explain that in a second. Let me just write this down, and then I'll explain what I'm writing here. So we're going to do the exact same thing, but now instead of explicitly saying things have to be equal, we're just going to put inequality constraints. So I'm going to set this epsilon to 0.5, and then I'm going to take our original equation, which said that the coefficient of x and y have to be equal and opposite in that first equation. But instead of that, I'm now going to say they just have to be equal and opposite within a value of 0.5. So I'm giving them some leeway to actually not be equal and opposite, but still within some specified range that I want them to be close to one another. And this gives them a little bit more leeway and the optimization a little more care to actually fit the data well. So that's what I'm going to do with the first coefficient. The second one is exactly the same, except for equal to 28. It's going to be less than, that coefficient needs to be less than or equal to 28, but otherwise exactly the same. So I think we can just rerun this now with inequality constraints. And it ran. It looks hard to figure out what's going on here. but we can actually get a lot of insight into if we plot all the data together. So let's see, I have a function for that. So make 3D plots, xtest, xsim, x constrained, sim, last label, right. Okay, so last label is this thing. It's very hard to do without a mouse. Okay. Okay, so this is what it looks like with the inequality constraints. What does it look like with the equality constraints? So actually, I need to rerun this since this is, I overwrote the previous value. So let me rerun the equality constraints, the inequality constraints, and then show you what that looks like. Okay, so this is the results on a testing Lorenz trajectory using the constrained SR3 model with the equality constraints. And you can see it's totally screwing up. And the problem is you have these hard constraints, but there is noise on this data. It's not perfectly, the time steps are finite. So actually putting those hard constraints can actually pull you away off the data and do some sort of unphysical things. So actually, inequality constraints tend to work better for noisy data. So if I now plot the inequality results, absolutely gets it correct. So actually giving the optimization algorithm some leeway to sort of get within a range of the values you expect from your prior physical constraints actually gives you better models than if you just say this is exactly what it should be, despite your data having noise, having different errors in it. So this is really the point I want to drive home, is that inequality constraints in general are going to be more robust in the presence of noise. So that's what I wanted to show for part 2D. And then 2E is using trapping PySINdy to get globally stable models. So I'll go over that now. So trapping PySINdy is a little bit different. It's adding some extra loss terms here that actually promote globally stable models. This only works for certain types of fluid flows and plasma flows, so you can't use this for everything. But I just want to demonstrate it because it does show how you can get stable models no matter what new testing trajectory you work on, and that can be really useful when you have noisy data. So I'm just going to set lambda here to 0 because if you promote this stability, you often can get provably stable models without any sparsity promotion whatsoever. We're going to run this algorithm for 20,000 iterations. And then I'm just going to set this hyperparameter, which is not super important for us. I'm going to set some constraints, which again are not super important here. And then I'm going to define the optimizer that we want. So it's called trapping SR3. We're going to set that threshold, set eta, set the constraint right-hand side and constraint left-hand side. And then I also need to reorder the constraints, but again, that's super important. I just want to show you sort of the types of things that you get with this. And a couple other hyperparameters here. So setting this hyperparameter gamma to -1 and then saying the max iterations is 20,000 here. Then we also need a PySINdy library, and actually this we do with a custom library. So I'm going to say library functions, and I'm going to use what are called lambda functions in Python. And here I'm just asking for basically linear functions. So whatever x is, it's just going to produce linear functions of that variable. And then same thing with, I'm going to ask for quadratic polynomials with this notation. Whoop. And then exact same thing. So I'm going to say library function name. So I'm just calling these functions different things. So this is going to be called x. This is going to be xy. This is going to be x plus x. Okay. All right. This is not super important. Basically, I'm defining a quadratic polynomial library using a custom library. And the reason is I want a particular order of the terms for the constraint I'm putting in. But again, not the most important thing. Now I need to actually build the library with these functions. So library functions equals library functions. And function names equals library function names. Okay, so built the custom library. Now we can finally fit our model. Let's see. We're still using those feature names, XYZ from Lorenz, defining our optimizer, and putting in our feature library that we just defined. And then we have the model. We can fit the data. And print. And then we found the model, and then I have a routine to actually check, are these models provably globally stable? And I won't go into the mathematics there. I just have a function that tells us one way or another if it's the case. So I'm going to extract the coefficients from the model, and then I'm just going to use this function check stability and send it some of the information. So let's see if this runs. Yes, this should be 3. So R here is just the size of our system. So we have a 3-dimensional system of ODEs. Okay. Constraint matrix should be defined. Oh, I got these backwards. This is a good lesson, and I am quite fallible with code too. So sending the constraint left-hand side to this constraint matrix I've defined here. Okay, so now it's running. It's going to run for 20,000 iterations. It's printing out its progress every 2,000. You can see both the error in the data and the error in the stability are decreasing in time as we run this. Okay, so it turns out, so the answer, if this is globally stable, is if all these values here are negative. And so it says all AS algebras are less than 0, and therefore system is globally stable. Okay, that's true. It checks this. Okay, so the model we got is actually provably globally stable, and turns out it's this thing. There's some extra small terms here, but actually you can remove some of these by just converging the algorithm for some more iterations, like 40,000 or 60,000 iterations. It'll sort of converge these terms down. But nicely, we've gotten a model that's actually provably stable for any new testing trajectory. So we can actually check that for a large number of trajectories. So let's make that plot. So apologies for the plotting details here, but this will help us visualize what's going on. Big dot add subplot. Okay. So we're going to try 10 initial conditions. And each of these initial conditions is going to be between minus 100 and 100. So each of the XYZ initial conditions is going to be between minus 100 and 100. And then we're going to sort of take that new value, use solve IVP to integrate the Lorenz system for that new initial condition. So again, don't pay too much attention to the evaluation here, because this is just making the data. Okay, so I have a new trajectory. Now we want to plot that trajectory. Let's just copy and paste this. So we're plotting the new x, y, and z trajectory in 3D space. And the plot will be a little easier to explain in a moment. So we'll plot the new trajectory in black, and then we're going to get our predicted trajectory by simulating our model with this new initial condition, again on the same time base, and we'll just use I'm not sure why I did this, but using the ODE int integrator instead of solve IVP, but either way. And then once again, plot the same thing. Let's copy and paste this over. But let's make the new data blue so we can see the difference. Let's put this down here. Great. Okay, so hopefully that will run. It'll take a second to generate and simulate these 10 new trajectories. So bear with me here. But we're going to see this nice plot. So what you're seeing is, again, the black trajectories are the new testing trajectories on the Lorenz system, and the blue trajectories are the same thing for the trapping PySINDy model that we identified. And you can see no matter how far you start away from the Lorenz system, all the trajectories fall into the middle and then correctly get onto this nice Lorenz attractor that we would expect. And this is these models are actually provably stable, so you can take infinitely far initial conditions, it'll still fall in. The reason there are some differences in the trajectories here is just that, one, we didn't converge the algorithm very far, and also the time steps out here are not small enough to like really fit these trajectories that are way out here. But you can fix this easily. I just wanted to show that no matter what initial condition you start out with, these sorts of models fall right into the attractor that you expect. So this, again, can be useful for noisy data, and in general, building these sorts of stability constraints into system identification can be really powerful. So thanks for listening, and I'll finish off part 2 and start part 3 in the next video.